Okay, hello. And in this video, we're going to go over some matrix systems in part of the exam. So this problem is from the 2024 to the 2025 exam in February. It's problem number 1. And yeah, let's see what Aarhus exams are all about. So we have this problem over here, and I'm gonna do them one by one. So number 1 first. I went over this in my other matrix videos, but number 1 is write the system of equations in matrix form. So as per my other videos, I have talked about how the coefficient matrix is made from the numbers multiplying the variables. So what I mean is that first we have to write out the augmented matrix, which is A equals, and then to write the augmented matrix, we take the coefficients. So 6, 2, lambda, and 1. And then now we have to write the variable matrix. The variable matrix is the variable being used, which is x. So we have a variable matrix, and then the variables being used are x of 1 and x of 2. And lastly, we have to write a constant matrix. The constant matrix is the answers on the right-hand side. So we see 3 and 1 on the right-hand side, so we write that down. So now we can write the full matrix equation. Ax equals b, as I was pointing out quite a bit. So the whole matrix equation is 6, 2, negative lambda, 1, times x of 1, x of 2, equals 3 and 1. And that is the answer for number 1. And it is that simple. So now I'm going to erase a little bit and go on to number 2. So number 2, for which values of lambda does a system of equations have one unique solution? So I want you to remember that a system has one unique solution if the determinant is not 0. I have stressed that a lot in my other videos. So step 1, we have to find the determinant then. And remember, for a 2 by 2 matrix, the determinant is AD minus BC. So as again, I'm going to rewrite our augmented matrix. 6, 2, negative lambda, 1. So here our determinant would then be 6 times 1 minus negative lambda times 2, which would then become, 6 times 1 minus negative lambda times 2, which would then become 6 plus 2 lambda, because 2 negatives make a positive. Now we have to set the determinant not equal to 0, because a system has one unique solution if the determinant is not 0. So we have to set it equal to not 0, does not equal 0. And now we can solve. And so we want to isolate the lambda. So this becomes 2 lambda does not equal negative 6. And now to isolate the lambda, we can divide both sides by 2. So this becomes lambda does not equal negative 3. And that's it. So that's the whole answer for number 2. So there is one unique solution whenever lambda does not equal negative 3, is how you would write it. So now let's move on to number 3. Find the inverse matrix. So I had a whole video on inverse matrices, so if we forget, we can go back to that. But for any matrix A, B, C, D, we remember that the inverse is 1 over the determinant, and when we swap the diagonals, and then we negate the other diagonals, remember? So here, our augmented matrix is 6, 2, negative lambda, and 1. So the determinant is, as we as we discovered before, the determinant is 6 plus 2 lambda, right? Now I have to swap the diagonal entries. So we swap 6 and 1. And then we have to change the signs of the other two entries. So we have to change this to a positive and change this to a negative. So our inverse matrix will be 1 over 6 plus 2 lambda. And then 1 lambda, negative 2, 6. And that is our inverse matrix. And that's the solution to number 3. Now let us move on to number 4. Number 4 says find the solution to the system of equations for lambda equals 2. If no unique solution exists, then is there no solution or are there infinitely many solutions? So there's kind of two parts, and it's basically the exact same concept as number 5 as well. First things first, we have to substitute lambda equals 2 as it says, right? So when we substitute it, the equations then become 6x1 minus 2x2 equals 3, and 2x1 plus x2 equals 1. So step 1, we have to solve the second equation. We have to solve it for x2 so that we can substitute it back. Because what we're doing here is we're basically solving a system of linear equations. So when we look at equation number 2, to isolate it, we have to move this to the right side. So x2 equals 1 minus 2x1. And now we can substitute that into our first equation when we see x2. So we have 6x1 minus 2 times 1 minus 2x1 equals 3, right? Now what we can do is we can combine the like terms. Or no, first we have to distribute the 2, right? We have to distribute to our parentheses as we've learned. 6x1 minus 2 plus 4x1 equals 3. Now we can combine the like terms, which are these. So this becomes 10x1 minus 2 equals 3. Now we can move 2 to the other side to isolate x1 more, equals 5. And now we can divide both sides by 10 to really isolate x1. So x1 becomes 1/2. But we're not done here. When x1 is 1/2, we need to find x2 as well. But we have this equation over here that we isolated x2 in, that we can sub x1 into that. So x2 equals 1 minus 2 times 1/2 from here, which equals to 1 minus 1, which equals 0. So our answer for number 4 is that x1 equals 1/2 and x2 equals 0. But wait, we're not done yet, because the second part of the problem still exists. We have to get the determinant of the set of equations. And to get the determinant of the set of equations, we use our same formula, 1 over AD minus BC, right? So when you apply that formula, I'm going to put it over here. The determinant is 6 plus 2 times 2, which equals 10, which does not equal 0. So because the determinant does not equal 0, there is a unique solution. So that's the answer to the second part, and the answer to the first part is x1 equals 1/2 and x2 equals 0. So now we'll look on to the fifth and final step. I should in reality make you do this on your own, but because I'm a very nice girl, a nice daughter, and a good citizen, I will be doing this with you for now. But number 5, as you can notice, is going to be the same exact pattern and steps as number 4, except substituting a different number. And this is what's kind of nice about exams like this, is that once you know how to do one part, you know how to do like the other part, basically. So when you substitute lambda equals -3, the equations become 6x1 minus -3x2 equals 3. And the second equation becomes 2x1 plus x2 equals 1. Now we can simplify the equations because as you realize, the double negatives make a positive. So we have 6x1 plus 3x2 equals 3. And this one can stay the same. 2x1 plus x2 equals 1. Now, something we can realize is that when we multiply the second equation by 3, I want us to realize something. When we multiply the second equation by 3, we get 6x1 plus 3x2 equals 3. I want you to realize how this is exactly the same as the first equation. So because both equations are the same, exact same, and they're the same line, what this means is that there are infinitely many solutions. And that is the answer to number 5. And yeah. So we can actually write the solutions using one variable. And this is not something that you need to do, but this is something that I guess I realize. So from 2x1 plus x2 equals 1, we can solve for x2 as per usual, right? So when we solve for x2, we get 1 minus 2x1. And then we can let x1 equals t when we parameterize the equations. And when we let x1 equals t, because t is our usual variable we use when we parameterize equations, I don't really know how Aarhus works or how Denmark works, but it's a bit weird. So if I were you, I would just stop at infinitely many solutions. But depending on what they request, you may have to parameterize the equations and write the solutions using one variable. But when you do that, you have to let x of 1 equal t to parameterize it. And then when you have that, we have x of 1 equals t, and we have x of 2 equals 1 minus 2t. So we're replacing this with just 1 minus 2t as we have this be t. And this is called parameterization. If you want, I can cover a video on that, but I don't think you'll have to do this. I personally wouldn't request that my students do this as well, so I wouldn't do that if I were you. And by the way, t here is any real number. And that's it. That is all the 5 solutions to 1, 2, 3, 4, 5 for this problem number 1. And yeah. Well, I will go get a fucking I don't know. I'm gonna go get some marshmallows or something.